You enjoyed the cheese. All right, there you go.
Hey, Michael, ready to start now, or what should I? You ready to go? Good to start? Okay. And we're actually going to start paving some framework to implementing your own crypto, because I know you're not supposed to do that, but we're going to talk about that anyway, because it's CypherCon and we can. And we're somehow going to try to squeeze some of this into 20 minutes. All right, good to go, Adrian? Oh, you're recording. Oh, okay, I'm so sorry. All right, so this talk is no encrypted data on this drive, just pictures of my cat, because that's what fills up people's hard drives and has the most innocent looking stuff. It's just random lolcats from the internet. But when you're looking for encrypted data and it doesn't look like encrypted data, it's a lot harder to find and you can easily deny it. None of this work is with any groups I'm affiliated with, any companies. It's just me. All right, so modern crypto is not designed to hide itself. A lot of times when people use SSL or TLS, everyone knows it's an encrypted transmission, but that's fine. It's not how it's designed to be. So what we need to figure out, because there's right now, people are afraid of crypto, and essentially they find ways to rubber hose it, which is the attack where you hit someone with a rubber hose till they give you the key, which is the most effective tactic in crypto, except CyDragon actually gave me a more effective technique, and we'll talk about that in a little bit. So, but also, not all ciphers are as secure as possible. Performance matters a lot. AES was chosen with performance in mind in addition to speed. So it's not all about security. So crypto doesn't hide its own existence. It doesn't pretend it's something it's not. It just says, hey, I'm sending data. Bob, I'm sending data to you from Alice. It's definitely me, but I don't want Eve reading it. Not, I'm passing you a note and you're not seeing it, and no one else sees that it even exists. So how do we extend this, and how do we defeat the rubber hose attack? So that's our goal today, and we want to hide from a machine and hide from a human, which is actually very different, as we will go into. So what is the rubber hose attack? So this XKCD pretty much sums up the most powerful attack on crypto. Though also that guy should not have been using RSA. That was the wrong cipher. You want to use a public key there, and it's too slow. But besides that, the hammer works very well. So what are the two main methods to defeat this rubber hose attack? We don't want them looking at that we don't even want them to know there's encrypted data. Because if they're not looking for something, why are they gonna hit you with a rubber hose? Oh, wrong way, sorry. So what are we seeing in real life? Stop the rubber hose attack. There's also another way is to make it look like something else, but you don't want them to even think that the data is there. So the big issue today in privacy right now is the idea of forced key escrow, which is essentially a rubber hose attack. If you don't give the private key to some government agency, we'll hit you with a rubber hose or shoot you or put you in prison until you give the key. So it's the exact same thing. And so that comes in with Apple versus FBI. The FBI is attempting the rubber hose attack on Apple. And it is definitely the biggest threat to crypto, because also, crypto is very, very strong, and the math actually works, which makes some people very scared. So there are two methods, nothing to see here, that you don't want the fire behind you, so that's bad steganography there on top of that sheet. But also, sometimes if you're trying to pretend that you're giving something, make it look like you're giving something embarrassing. Like maybe there's stego in that image, but you're pretending that the cat is being incriminated by hurting the rabbit, even though the rabbit's asleep in real life when that picture was taken. So what are the main differences between humans and machines? Well, sometimes you can use weird patterns like fake drunk type and making something look like it's actually text, but the machines will be fooled. But humans, they have time, they know where to look, they have human intuition. Like, for example, and this was, hang on one second, it's probably nice. So, thanks, in the spirit of the keynote, and also because I screwed up with LaTeX and not getting it to load Chinese characters, but using the wrong character there with Yishengoma, or Yishengoma. I'm sorry for my horrible pronunciation, I'm just learning, but that goes from, do you miss me, to, you miss my mom. Now, a machine won't necessarily get that, and true story, by the way, I messed that up once when I was talking with someone, so, yes. And I realized, wait, changing characters, that's actually a stego technique that machines won't get. But humans might, though not all humans, but the Chinese that everyone's afraid of, they will get it, I guess, in the spirit of our keynote. And so, what steganography is about is, it's essentially security by obscurity, right? You don't want them to know the message is there. It can look like something else. Usually with CTFs, it's all, oh, it's an image and least significant bits, because theoretically that's the best stego, but everyone knows where to find the bits. And then, if you know stego is there, the stego has failed. Even if it's encrypted data and you can't decrypt it, the ciphertext is available and the person can get rubber hosed for the private key. So that's a failure there. So what do you want to do? You want to make it look like legitimate looking files. Pictures, lolcats, I has your data and emailing that out, that won't get caught. Text is very good, no one suspects text. And sadly, we don't have time for a demo, but one of my favorites is an encoder that makes everything in white space. And then you can just put text all over everywhere and no one knows what's there. And so essentially anything that sends bytes anywhere, you can change them and make it look like something else. If you're following an RFC, all the better when you're sending data over the wire, because it looks like something else. So no one will suspect anything because you're following the standards, but you're really not. You're sending data out of channel. So even if there's something like a key escrow, well, you're not sending with SSL. You can even encrypt your data, but you're sending it out of channel. Some people say, well, if you pre-encrypt, any SSL inspection will catch that. Well, not if it looks like a DNS query, not if it looks like you're emailing a cat picture. No DLP will catch that, despite what all those vendors at RSA will tell you. So, it's easy to lie about what something is, right? We don't want people to know that's data. Is it a text file that might contain the launch codes that you're getting beaten up until you give that? So, the nice thing about XORs, so the one-time pad is the greatest cipher. It is mathematically the perfect cipher, and we'll get into that later. But you can essentially make anything look like anything. You can take a tarball and turn it into a PNG file because you're just XORing all the bytes. So you can just, essentially, it is a perfect cipher and you have no idea, it's mathematically provable that you have no idea what's there because you can manipulate any byte any way. So essentially, this is perfect. Now, before we go in there, here's what you should not do with stego. Essentially, don't make them CTF problems. CTF problems have to be solvable. You want security by obscurity. It's your only way. It's not like, oh, security by obscurity is not ideal. If you don't have the obscurity, you've failed. And if you're going for machine, you're going for machine rubber hoses, essentially SSL inspection is the way I think of that. You end up, it doesn't even have to be a good picture, so you can speed up data transmission that way. Against a human, that's different. So the one-time pad, and this lets us prove that such a cipher is possible, and then we will go into how to make it more practical. Because this is not practical because the key has to be as long as the message. Having said that, it is the absolute perfect cipher. All the key is the plaintext or the ciphertext. So you could even have two plaintexts and the keys can be different. You can store them somewhere else, maybe on one iPhone that the FBI doesn't get, it goes to the right data, and then you store it on another iPhone that doesn't have a lock and give that one to the FBI, and then they'll decrypt it to the wrong ciphertext. So, one idea. And one issue with the one-time pad, the one big issue is if you're using a bad random number generator, you're not going to have a good time. So, true random is possible. There are some people working on true random number generators. Essentially what you do is you split a beam. The number of photons should be divided evenly, but it actually fluctuates with the Gaussian random distribution, and this is because of quantum mechanics. So you actually can create quantum random noise. So this cipher actually becomes usable and practical. And what's so beautiful about this is it is the perfect cipher for stego too, because you can pick any file you want that can be as innocent looking as you want, and it can be something else. I mean, you can turn a Word doc into, or a text file that has all your secret data into some random Word doc where you're writing a relative and, working on something or working on a letter. I don't know, but you can essentially, you have an infinite amount of choices. They're not infinite, but you have 2 to the n choices, and there's 2 to the n possible bit strings in any file based on the size. So you have 100%, essentially 100% control, 100% entropy, which you can't get any better than. And so what we're trying to do is you can easily have 2 plain texts. So one thing you could do is you could compress the key into a zip file and put a password, but the problem is you need 2 keys, right? If you have one file, and if you have 2 different files with the keys that are compressed, someone might find that other file. That's not good. So what you can actually do is put static keys in the file, which is normally bad. But in this case, if you hide the key and the password tells you where the key is, now you have m choose n possibilities of where the bytes are the actual key. And we're actually going to even find ways to speed this up, because as awesome as the one-time pad is, we can't necessarily use that for everything. So we want to start using the OTP, but if we have different keys, we can run into some detectability issues. So how about we use different bytes of the file? So if you have different bytes of the file, you can choose which bytes go to one plaintext, which bytes go to the other plaintext, which is similar to how TrueCrypt pulled this off. And so you can even encrypt it with an AES or a Salsa 20. Salsa 20 is essentially a stream cipher that's better than AES and faster, and I wish people would use it more. And obscurity is actually real security, as I'm saying, because you have m choose n possibilities, which with a big file, m choose n is a big number, because factorials are very big. So there's lots of different possibilities of where your key actually is. So we want to shrink this key down. So we're going to put this in, and we can't really do any demos, and I know this is kind of fast, but I'm just trying to squeeze this into 20 minutes and do kind of an overview today. But you end up taking your key, put it in the file in random bytes. Those bytes will get discarded at the end, and the other bytes that you don't need from the other plaintext, or the other data that you don't want, and you create an integer sequence. You create a finite group that you can go through the file, and usually a cyclic group is very computationally efficient, and you can go through parts of the file and grab the bytes you need from each cipher, and grab the key from different parts of the file. So the key is in there, the data is in there, but different passwords unlock different keys, because if you put the key in a different part of a file, you end up being able to extract different parts of the file with different passwords. So how do we generate these sequences? Just so this is a math review of this. So prime number sequences, just prime powers, they'll never overlap. You have an easy integer sequence. If you pick a primitive root, mod n, you will be able to get phi of n values as a subgroup of those numbers, and so you can grab those bytes. And phi of n is a decent size, usually of n. It's up to n minus 1 if n is prime. So, but even then, even if n is prime, which is a worst case scenario for which bytes are used, you still have a lot of different possibilities of where the bytes are that you want, because n choose phi of n would be n choose n minus 1, which is a large number, especially with bigger files. And unlike a lot of crypto, the bigger the files, the more secure it is, which is slightly different because a lot of crypto attacks work with larger files. You end up being able to guess plain text. So it's kind of a little counterintuitive here. Okay, crap. How do I get that? Oh, there we go. So if we're not using all the bytes, we can add more obscurity, which will help because then it's a lot harder to find the actual data. It'll make a forensics person very angry. And the other nice thing about that is there is absolutely no way to prove that there is or isn't data on there. And if you have a lot of junk bytes, well, that could be a third plain text. We don't even know. And we'll go into the advantages of that later for a scenario on how someone could possibly defeat a rubber hose in using such a cipher. And another method, if you want to make use of space, is just add to prime powers, like add a certain value that obfuscates further, but then you can still end up using more of that. You can end up using more of that file. And what's beautiful is you're creating isomorphic groups, so the algorithm's the same, everything is the same, you're just adding a certain value, and nothing really changes, which makes life a lot easier. So some tips and tricks with these kinds of ciphers, and I mean this is brand new stuff that I've just started playing with, so it's kind of fun to share, but using primitive roots will get you more bytes. Because you want an easy sequence to predict, because if you have a long sequence, or a random sequence, then you need more data to go into that key. And what we really want is someone under pressure, they need to be able to generate a key from their password and remember 2 passwords. How am I doing on time? Okay, I'll keep going. Okay, that's fine. So this is where the hard part is, because static keys generally are very, very bad in crypto. Like, even if you're a non-crypto person, if you've ever reverse engineered any executable, people find static keys or static passwords, and that's very, very bad. But here, we need some way to decrypt it so that it only takes a password, and to keep the randomness, we have to have the keys in the file. So, again, it's security by obscurity. But if you have enough obscurity, you will actually be able to hide the keys, because the password's the bytes, and you're actually using the obscurity to hide your static keys, but actually obfuscate well enough, because obfuscating your code won't work. But if it's random bytes, then you actually have real obfuscation here, and you turn something that used to be very, very bad in crypto to something that's actually acceptable and usable. So, we might have a little bit of time for questions. I don't know how well I'm doing on time, but this is the real life method I could think of in this. Is you have to choose integer sequences for certain bytes, and you want 3 different plain texts. So you want to have one plain text is the super innocent one, like, remember the kittens, no, nothing bad at all. And then you're like, okay, then the person who has the gun to your head says, no, I know you know these techniques, so show me the real one. And then you show them one that's semi-incriminating. If you've ever seen the old show Burn Notice, where the guy says, if you want someone to believe a lie, make them work for it. So you'd be, all right, I'll give you the real one, I admit it. You give them a second one, and it's kind of embarrassing, something you don't want them to see. But then the rest of the real data is not shown to them, and they think they've gotten it, and then they leave you alone. So that's a real life scenario I could see where someone could actually use 3 different plain texts and be able to get out of a true rubber hose scenario. I don't know if we have any time for any questions. Are there any questions? Actually, wait, so QR code time. Sorry, I forgot about that. QR code if anyone's playing. And I have everyone have the QR code that they need?
You scored 007, right? I do 007.
I don't know. This guy gave it to me. Maybe James Bond has been rubber hosed before, so maybe that's why. He's generally good at getting out of it too. And contact info, my email, if you need to get a hold of me. And if you spam me, don't do that.
I think he needs a beer.